So this is about discretizing a field theory, which is usually defined in 1, 2, 3, 4 dimensions, but to make life simple, it's defined here in 1 dimension. And field means that at every point on the floor, which is this vertical horizontal axis, there is a function called field, which is, you can think of it as a blade of grass, and this is how high this blade of grass is. So this is the Germans invented it thinking of real fields with grass on it. So that's what it is. Now, if your Euler says your function is very hard, let me just put little columns, discretize it. And that's called discrete field theories. So it's put on a lattice. And if you take unit of length such that the separation between your 2 points on lattice is 1, this is an integer lattice. So it's very naturally labeled by integers. So a field is the value of this function from minus to plus infinity on the lattice, on the integer lattice. So this is totally intrinsically infinite problem because you have infinitely many numbers to deal with. And because you have translation invariance, what physicists always do is they say, well, you know, this is very long, infinity from plus to minus infinity. So let me put it in a box, but violate translation invariance as little as possible. As little as possible means I will put this infinite line, I'll curl it into a ring of size n, and rotation on the ring will be translations, so nice translation properties will be preserved. But now I've made this a finite field theory, and that's how all the calculations are done. That's how quantum mechanics quantize is anything, you know, when you have scattering problems. You put them in a box, make the box periodic. Eventually, you take the limit where lattice spacing is small and you worry about it, but you won't do that here now. We'll really take the lattice seriously. If you're condensed matter physicist, lattice exists. If you're doing metamaterials, lattice exists. It's the size of the basic cell, and that's a fact of life. That was figure number 1.